Hi everyone, here is our fourth chapter, Aqueous Solutions. Okay, let's remember 9th grade, 10th grade, what was solvent, what was solute, and let's start with an example. For example, if you have a salty water here, salt will be the solute where water will be the solvent, or you can have natural gas. Natural gas mostly contains methane gas, and the solutes can be ethane, propane. So when I say solution, please do not only understand salty water, sugar and water. Gas-gas mixtures are also solutions, or alloys are also solutions. For instance, brass. This is composed of zinc and copper, and zinc is the solute where copper is the solvent. So this is an example for solid plus liquid. This is gas plus gas, and this is solid plus solid. Let's remember the solubility rule. Solubility rule says like dissolves in like, meaning polar substances can be dissolved in polar solvents, where nonpolar substances can be dissolved in nonpolar solvents. And if you have an ionic substance like salt, sodium chloride, it also needs polar solvents. Now you can see that ionic dissolving here. For example, you have barium chloride is dissolved in water. You have the barium 2 plus, chlorine minus 1 and chlorine minus 1, and they are surrounded by these water molecules here. So surrounding of an ion by water molecule is called hydration. If another solvent other than water is used, the name of this dissolving process is solvation. So when you dissolve barium chloride in water, remember we just have talked about interactions between the chemical species in 9th grade, and also we talked about them in 10th grade chemistry lectures. When you dissolve barium chloride in water, ion dipole interaction causes the dissolving process. Okay, let's say that you have a solute here and you have a solvent here. And this solute seems to have a solid form. So the distance between these solids is going to be just opened up. So this means that you need to give some amount of energy to it. So you have a delta H value here. Delta H means heat difference in order to just open the distances between the solid particles. And what about solvent here? It seems like water molecule. So in order to just make these particles separated from each other, you have to give some heat also. Let's say that this is delta H2. Now they are going to be attracted by each other. So this attraction probably needs another heat difference, delta H3. So now that the dissolving process occurred, so you have heat of dissolving here. So heat of dissolving is equal to sum of these heat differences, delta H1 plus delta H2 plus delta H3. So these values can be negative, positive. It depends on whether they are exothermic or endothermic changes. So how do we classify these heats? The amount of heat taken in or given out when 1 mole of substance is dissolved in a solvent is called heat of dissolving. If the interaction between the solid and solvent particles is stronger than their separate intermolecular interactions, then dissolving is said to be exothermic. If the interaction between solid and solvent particles is weaker than their separate intermolecular interactions, then dissolving is endothermic. If two liquids can be dissolved in each other with every ratio, they are called as miscible liquids. And finally, the solutions that conduct electricity is known as electrolyte liquids, like acid and water, salt and water, base and water. They are known as electrolyte because they can conduct electricity. Now here is the units of concentrations. In fact, I'm going to pass them quickly because you have learned most of them last year in mixtures unit. But let's give just their formulas only. Mass percentage. When you calculate mass percentage, you need mass of solute over mass of solution times 100. When you calculate mass of solution, you're going to add mass of solute with the mass of solvent. Now comes the volume percentage. It is just same as the mass percentage. You have volume of solute over volume of solution times 100. But in this case, finding the volume of solution is not that easy as the finding the mass of the solution, because when you sum the volumes up, they are not going to give you an exact number. So in most of the questions, the exact volume of the solution is given to you. Now here is something new. This is called as the mole ratio. For example, in a container, you have 1 mole of sodium chloride, which is dissolved in 9 moles of water. Mole ratio is just shown with capital X here. For example, mole ratio of sodium chloride is equal to 1 over 10, meaning mole number of solute over total mole number. And mole ratio of water is equal to 9 over 10, mole number of water over total mole number. And when you sum them up, you're going to see that this is always equal to 1. So mole ratio of the components of a solution should be equal to 1 always. And now comes something familiar. This is ppm and ppb. ppm is parts per million, where ppb is parts per billion. So when you like to find the ppm, you're going to find the mass of solute in 10 to the power of 6 grams or kilograms of solution. And we have done it last year, please remember it. And parts per billion, you're going to look for 10 to the power of 9 grams or kilograms of solution. So it is just same as the mass percentage. But in some occasions, in fact, the SI unit of ppm is milligram per liter, and for ppb is microgram per liter. So this is the volume of solution. This is the mass of solutes, and the same thing is valid for this ppb here. So for instance, you are given 4 decimeter cube of solution, and it contains 2 grams of, let's say, chlorine gas. And if the ppm asked, here is your ratio. 4 decimeter cube means 4 liter. Please be familiar with the volume unit conversions. 4 liter contains 2000 milligram of chlorine. Remember, I have to take that unit in milligram here. So what about in 1 liter? So you're going to find it as 500 ppm. So if mass ppm is asked something different, you're going to do. If mass per volume ppm is asked, something different that you're going to do. Now, molarity concentrations is really important for us because we are going to use them a lot in the next chapters, in the equilibrium chapters. This is the mole number of solute that is dissolved in 1 liter of solution. So molarity is equal to mole over volume. This has a unit of mole. This always has a unit of liter. So the unit becomes mole per liter, or mostly you're going to see it as molar here with a capital M. And the word is really familiar with the molarity, which is molality. Again, it is the mole number of solute that is dissolved in 1 kilogram of solvent. Please be careful with this value. 1 liter of solution and 1 kilogram of solvent. And molality as a formula, this is mole number of solute over mass of solvents in kilograms. So mole per kilogram can be its unit, but usually we're going to write it as the small m here, meaning molal. This was molar and this is molal. So diluting, concentrating and mixing the solutions. Adding or evaporating water will dilute or concentrate a solution where the mole number of the solute will stay constant. For example, you have a solution like this, and let's say that this is sodium chloride, and you add some water into it, and it becomes like this. So this means that you diluted the solution. So when we dilute the solution, what kind of quantitative property does not change? Of course, it is the mole number of solute. So you can write an equalization like this. Mole number 1 is equal to mole number 2. So when you change the amount of water only, you can formalize it as molarity 1 volume 1 is equal to molarity 2 times volume 2. If and only if the amount of the volume of water is changed, you can use this formula. Colligator properties. The properties that depend on concentration of solution is known as the colligator properties. These can be classified as decrease in vapor pressure, then increase in boiling point, decrease in freezing point, and osmotic pressure. Let's look them in detail. If some amount of a non-volatile substance is dissolved in a liquid, the vapor pressure of the liquid decreases. The amount of change in the vapor pressure depends on concentration of the solution. Rolle's law is used to calculate the vapor pressure of a solution. So there are two situations. There can be a solid dissolving in a liquid, or there can be a liquid dissolved in another liquid. So if there is a solid dissolved in one liquid, vapor pressure of the solution is equal to mole ratio of that liquid times vapor pressure of that liquid at that temperature. So you do not take that solid and contrarily, because solid has no vapor pressure, so you're only looking at the vapor pressure of that liquid. So if you have two liquids, in this case you have two different kinds of vapor pressures, so this formula is going to be get larger. Vapor pressure of solution is equal to X liquids 1 times that liquid's vapor pressure at that temperature plus X liquid 2 times vapor pressure of that liquid at that temperature again. So this is how to calculate the vapor pressure of a solution. Increase in boiling point. Temperature, when the boiling point means temperature of a liquid at which vapor pressure of that liquid is equal to atmospheric pressure. This is the definition of boiling point. So you can calculate increase in the boiling point like delta T is equal to K boiling times molarity times I here. So what are those? M is the molality. Let me explain you by examples. For example, if you have sodium chloride, you have two particles coming from it, so I will be equal to 2 here. Or if you have aluminum chloride, you have 4 particles, 4 ions coming from it, I will be equal to 4 here. So what about sugar? If you have glucose like this is a molecular dissolving. In this case, I will be equal to 1 here. So what about Kb here? Kb is temperature change when 1 mole of particle is dissolved in 1 kilogram of solvent. In fact, this temperature change, this is temperature, let's say, increased change, because we are talking about boiling point. What about decrease in freezing point? Decreasing freezing point can be calculated with the same formula, which is delta T is equal to, in this case you have Kf times again molality times again I here. So M again is the molality, I is, let's say that you have sodium sulfate in this case, and I will be equal to 3, and Kf is amount of temperature decrease when 1 mole of particle is dissolved in 1 kilogram of solvent. And final colligator property is osmotic pressure. Now, osmosis is a transfer of water from low concentration to high concentration. The pressure that is exerted by the high concentration part to low concentration part is called osmotic pressure. When osmosis starts, the water level on high concentrated side starts to increase. So this is hypotonic solution. You have less amount of solute per volume, and you have hypertonic solution. This means that this part is more concentrated part. And after a while, some water passes through the second part in order to equalize the molarities. And when the molarities are equal, then the solutions are said to be isotonic. So this is because of colligator property of the solution. Factors that affect solubility. First, type of substance. Type of substance means polar can be dissolved in polar solvents and non-polar can be dissolved in non-polar solvents. Again, like dissolves in like. What about temperature? If the dissolving is endothermic, as the temperature increases, solubility increases also. So you're going to have a graphic like this for solubility versus temperature. If it's exothermic, when the temperature is increased, in this case, solubility decreases. So you're going to have a graphic just vice versa, indirect ratio. All the dissolution of gases are exothermic. This is really important. So as the temperature increases, the solubility of the gases decreases. That's why we drink Coke cold. And the fishes are found in the deeper parts of the sea in summer. Now, what about liquids? Liquids a little bit different than the other ones. If the boiling point of solute is higher than boiling point of solvent, as the temperature increases, solubility increases also. If boiling point of solute is lower than that of solvent, as the temperature increases, the solubility decreases. We don't use that solubility rule for liquids that much, but if you have a question, please turn back to your handouts and check for the information, please. Pressure. Atmospheric pressure or any gas pressure doesn't have any effect on the solubility of the solids and liquid in water, but for gases, as the pressure increases, solubility of the gases increases also. Now, what about the common ion effect? Now, common ion effect is really important for us. We're going to just use them in the later chapters. And let me explain you briefly. We're going to just do some quantitative problems on that one also. Okay, for example, you have a pure water here. And you have another container with sodium chloride solution here. And you add potassium chloride into it. Let's compare their solubilities. Which one do you think will have more solubility than the other one? Now, the first one contains only water molecule, but the second one contains a common ion with the solute here. If there's a situation like this, the solubility of that solute is really lower than the solubility of that solute in pure water. So as the amount of common ion increases, solubility decreases that much. So the first one's solubility is really very high than second one's solubility. Now here are the final parts of this chapter, some important separation techniques, some of them that you have seen from last year 10th grade mixture, but some of them may be new. Okay, let's start with the extraction. For example, filter coffee or making Turkish coffee or just making tea, they're all types of extractions. But what about oil extraction? The seeds of plants are broken down and mixed with a good solvent for oil, which is usually hexane. The mixture is filtered. After that, by the help of a little heat, hexane is evaporated. Carbon dioxide extraction is used to obtain oil from seeds again. During this process, carbon dioxide dissolves the oil of broken down seeds. Why is that? Again, the same rule. Carbon dioxide is nonpolar and oil is nonpolar also, so carbon dioxide can be a good solvent. Or the most used technique is Socklet technique. Is used in order to separate the oil from plants like almonds, argan, rose, etc., which are willowy. Extraction of metals. In this process, an organic solvent is used for the extraction of metal. The aim is to separate the metals from the ore into another solvent. So you have that ore here, and in order to just purify this ore, you use some organic solvents. This is a kind of, again, extraction. So usually the metal is left alone after that extraction. So what about crystallization? For example, if you have salty water, if you just decrease the temperature step by step, after a while the solubility of the salt decreases. So some crystals just occur on the bottom of the container. So this is a crystallization. Or you can evaporate the water directly and leave the salt alone in this glassware. This is also a crystallization technique. Crystallization with a solvent. It's a method used for separating a solid homogeneous mixture into its components. The type of solvent that will be used is very important. This solvent should dissolve the desired solid very well at high temperatures, and the solubility of solid in that solvent should be very low, near to zero, at low temperatures. So when the mixture is dissolved in that hot solvent, the impurities are filtered, and when the mixture is cooled down, the pure solid is obtained. So this is different than the crystallization. Crystallization, there is, for example, salt and water. In this case, we have two solids forming an homogeneous mixture, but not like alloys. Just be careful with that. And you have fractional crystallization. Fractional crystallization is a method of separating mixture of soluble solids by dissolving them in suitable hot solvent and then lowering the temperature slowly. Now, crystallization with a solvent you use for solid-solid homogeneous mixture. This one, you use it for solid-solid, in this case, heterogeneous mixtures. And final one, probably we're going to do the experiment of it. Chromatography is a separation method especially of closely related compounds by allowing a solution or mixture to seep through an adsorbent such as clay, gel, or paper, so that each compound becomes adsorbed into a separate, often colored light. For example, you have a dye here, and you just let that dye going downwards, but the colors of this dye, green and red, their pigments, they have different rates. So as you see here, red just move faster than green one, so it's just goes faster downwards. So you just decompose this dye into its colors, like blue here, green here, red here. So this is called as kind of chromatography.